All right, here is a warm-up to curve sketching. Okay, so B1 is our next topic. And in B1, we're going to be able to sketch graphs of polynomials, rational functions for sure, and maybe some other types too, depending on how far you get. So let's just do a quick review of advanced functions. So everything you learned in advanced functions about curve sketching applies here. And then we're going to go a little deeper. So here's just like a crash course if you forget advanced functions. So you've got polynomial functions. If you recall from your previous math course, you can graph a polynomial function fairly accurately by looking at its degree, the leading coefficient, whether it's odd, even, positive, negative. And we can also use X and Y intercepts to graph it too. Okay, so we've got a first degree here, we've got a second degree, third degree, and a fourth degree polynomial. So here are things we know. The leading coefficient and the degree tell us about the shape and the quadrants that it's going to end up in. So basically, if you have a first degree equation, that's going to be a straight line. It's going to look like this. Now, the leading coefficient in this is a 1. And it's positive. So, oh yeah, that's all we care about for leading coefficients. Sorry, I was just blanking for a second. We just care if they're positive or negative. And for the degree, we care if it's even or odd. Okay, so we got a first degree polynomial with an odd degree. So we know that it's going to start down here in quadrant 3 and end up here in quadrant 1. Now, if we were to graph a first degree polynomial, but instead of y equals 1x, let's make it negative x. Now, because you have a negative leading coefficient, it's going to change your quadrants around. Now it's actually going to go in this direction. It's going to go quadrant 2 to quadrant 4. So let's move on to another odd degree polynomial, like the third degree polynomial. It functions in the same way as the first, with a shape slightly different. So since this guy has a leading coefficient that's positive, the same as our first degree one, the purple one, it's going to end up in quadrant 1 and 3 as well. But it's going to have a little bit of a curve on it. It's going to do something like that. But still, it's going to start in quadrant 3 and end in quadrant 1. So it's an odd degree. So odd degree polynomials always kind of start and end in the top and the bottom. So like if you consider this to be the bottom, then they're starting in the bottom and they're ending in the top. So they end in different spots. Okay, so that's what odd things do. They go from like the bottom of the graph to the top, or the top to the bottom. Now we figured out if the leading coefficient, so that was for odd degrees, we found out the leading coefficient, if it's positive, it goes from quadrant 1 to quadrant 3, or whatever way you want to look at it. And if it's negative, it's quadrant 2 to quadrant 4. Okay, so that's what we found out so far. Cool, so we could even hypothesize that if we had like an exponent 5 here, we know it's going to be quadrant 3 to quadrant 1, but probably have like, you know, a couple of these in between. Okay, but let's not graph that. It's not going to fit. Okay, cool. Ooh, so let's just look. So if our third degree polynomial was actually like y equals negative x cubed, then it's going to start in up there and finish down in quadrant 4. Okay, cool. So that's odd degree polynomials. Now let's say we're going to look at even degree polynomials. So like this one is even, and this one is even. Okay, so it turns out even degree polynomials are going to start and end in the same, like top of the graph or the bottom of the graph. So we know x squared is a parabola that looks like this. So it looks like it goes from quadrant 2 to quadrant 1. Okay, but what if we made it y equals negative x squared? Well, now I know that that graph actually looks like this. Okay, cool. So it looks like even either goes top to top or bottom to bottom. I don't know, that's probably bad terminology. So if it's an even degree, it does that. We see that the leading coefficient is positive, it's quadrant 2 and quadrant 1. And if it's negative, it's quadrant 3 and quadrant 4. Okay, so if we had x to the power of 4, positive leading coefficient, we know it has to start and end in quadrants 2 and 1. So it actually could look like a W, although I know that this one is actually just going to look like a really wide parabola, I think. And then if we actually had a graph of negative x to the power of 4, just do the same thing. Okay, cool. So that can totally help us just by like looking at the equation's degree. So first, second, third, or fourth degree. If it's even or odd, that can tell us a lot. And knowing if the leading coefficient is positive or negative, that's a ton of stuff right there. So we should be able to just look at a polynomial and kind of know what its graph might look like. Like for example, let's just say I wrote down like y equals 3x cubed plus 2x squared minus 5. And I'm like, oh my god, I have no idea what that graph looks like. Wait a minute, I have some idea. I can see here that it's an odd degree polynomial. So I know it's going to end like top and bottom or top to bottom or bottom to top. Then I look at my leading coefficient. I see I have a positive leading coefficient. So therefore I know I'm going from quadrant 3 to quadrant 1. So I know my graph, I have no idea, but it's going to look something like this. But like that doesn't tell me enough. Like I need to know, like, are there some maximums and minimums? Like, are there any roots or y-intercepts? Like there's lots more stuff that I can gather from this equation. But at least the shape of it is a start. Okay, so I'm just going to talk about rational functions really quick too. So if we had a rational function, I don't know if you recall this from advanced functions, but the thing that we care about for rational functions is the degree of the numerator versus the denominator. So if you look at our first example, number 1 here, the degree is the same in the top and bottom. So if it's the same in the top and bottom, P.S. I'm just going over this pretty quickly. Then there's some things that we know. Like we know all of these rational functions are going to make some kind of weird looking graph like that. Or sometimes, you know, remember they could have like a bunch of asymptotes and like look like this and then like this on each side. We know they're like those kind of like graphs that have asymptotes all over the place and look weird. So if you have the same degree in the top and bottom, which we have here, first I'm going to get some asymptotes. So to get my vertical asymptote, I always look at the denominator. That always gives you your vertical asymptote. So let's just get the vertical asymptotes of all these graphs right off the bat. Okay, so this one I can tell is going to be -1. Vertical asymptote occurs when the denominator is 0. So for the first equation, if x was equal to -1, -1 plus 1 would be 0. So I got an asymptote there. Question for number 2, I can't tell right off the bat, so I actually might want to factor it into x squared plus 2x. So I got x times x plus 2. So guess what? This one's kind of weird, but these x's actually can cancel out. So we're going to have a hole in our graph. Anytime something cancels on the top and the bottom, it produces a hole in your graph. And then that x plus 2 is going to give us our vertical asymptote at -2. Okay, cool. And then for graph number 3, I will have an asymptote at 1. Okay, so I got my vertical asymptotes just from looking at the denominator. Now to get my horizontal asymptotes, they're all different. So if the degree is the same in the top and bottom like it is for number 1, then the horizontal asymptote is going to be the ratio of the coefficients in front of x. So in this case, my horizontal asymptote is going to be 3, because these are my coefficients, 3 over 1, which equals 3. So I'm going to have a horizontal asymptote there. Another way to think about it is, as x gets really big, what is my function approaching? So if x was like 1 billion, my numerator would be 3 billion, and my denominator would be 1 billion plus 1 billion and 1. So what's 3 billion divided by 1 billion and 1? It's roughly 3. Okay, cool. And then I would just sub in some random value of x just to see like what my graph is doing on either sides of this asymptote. So for example, if x was 0, so that seems like a good one. 3 times 0 is 0, and 0 plus 1 is 1, so 0 divided by 1 is 0, so I'm going to have a point here. So my graph is probably looking like this, if I had to guess. Okay, cool. 1 down. Okay, number 2. So we find that if our degree is higher on the bottom, like in number 2, our horizontal asymptote is just at 0. Okay, which makes sense because as x gets really big on the bottom, then we'd be approaching 0. Okay, so then maybe I would just plug in some value for x. Like, I don't know. No. Well, I don't know. So let's just say we plug in 1. So 1 squared is 1 plus 2 times 1. So 3. So 1 over 3, so a third. Okay, so it's going to be here somewhere. Okay, so our graph's going to be up here. And then we'll have another segment probably over here, I would say. And then we're probably going to have a hole since we canceled out those 2 x's. Sorry. We're probably going to have a hole in our graph when x equals 0. So there'll be like some undefined thing right there. Okay, and then finally, the third case, when you have a higher degree on your numerator, that produces something called an oblique or a slant asymptote. I'm not going to get into that because I don't actually, like, it was covered in advanced functions, but it's time consuming. Like, you had to divide the numerator by the denominator to find your equation of your slant asymptote, but it ends up being like some asymptote like that. So then your graph ends up being like some weird thing like this. I don't know exactly, but we're not going to get into that because that's going to take forever. But there you go. Just a real quick, I tried, explanation of rational functions and how to kind of graph them quickly. You could also find the x and y intercepts, which I'm not getting into because if you don't know how to do that by now, you got to figure it out yourself. Okay, and then just really quickly, we have these 3 other functions that we could graph to if we wanted to. So radical functions, just to refresh your memory, kind of look like this, like half a parabola kind of. Exponential functions look like this if b is greater than 1. If not, it could be going in the other direction. And logarithmic functions are inverses of exponential functions. So it's like this kind of thing. And there you go. That's kind of what those guys look like. And in grade 11, you did a bunch of like those kind of things. Remember that? Okay, so we're not getting into that, but just so you remember kind of the basic shapes. Oh yeah, I was just gonna say, like, what if we had to graph f of x equals 2x cubed plus 4x squared? Like, let's just actually go ahead and graph that. Okie doke. So right off the bat, I can tell it's odd degree and it's a positive leading coefficient. So I know it's going from quadrant 3 to quadrant 1. I definitely know that. So something like this. But I want a more accurate picture. Okay, what if I wanted to find some x-intercepts? So that seems like a good idea. Actually, why don't we find the y-intercept first, because that's even easier. So we'll just sub 0 in. 2 times 0 cubed plus 4 times 0 squared would equal 0. Cool, so we got a point at 0, 0. That's good. And let's find, oops, I meant to sub in 0. Let's find the x-intercepts. So we definitely have one at 0. So we'll set y equal to 0. I'm going to factor out an x. So I'll have 2x squared plus 4x. Ooh, I might as well factor out a 2. Yes, I can. So 2x. Okay. Oh, why don't I factor out a 2x squared? Ugh. Sorry guys, it's late. Okay, there we go. Factor out 2x squared. Okay, now I set each term equal to 0 to 2x squared equals 0 and x plus 2 equals 0. So I know that x equals 0 and x equals negative 2 are my two x-intercepts. I already got one of them. And then when x equals negative 2, I have another one. Okay, and that's pretty much everything I can get right now with my limited skills here. So I know my graph's going to look something like this. But like, I don't know exactly. Like, what if it actually looks like this? Like, how would I know? Like, what's my missing information here? I'm missing these like peaks. Like, I don't know what they are. So we call these things like local max and minimums. Like a local maximum and a local minimum. So we're going to be able to use derivatives to now find those locations. And I'm going to save that for the next video. That was just a crash course in everything graphic.